Every fire truck in North America has a small brass cap screwed onto the female end of its bumper discharge port. Most people assume it's just a dust cover. It is not. That cap is an NST-threaded dead-end plug rated for 200 PSI, and without it, a fully charged hose line loses pressure in under 4 seconds. In this video, you'll learn exactly what that plug does under pressure, why the thread standard on it matters more than the brass itself, what happens when a department skips it, and which 1980s warehouse fire finally forced the issue nationwide. Fire hoses and their fittings look simple. 2 metal ends, a rubber gasket, done. But hydrant systems in most American cities run at 60 to 80 PSI static pressure, and a pumper truck pressurizes its own lines to between 150 and 200 PSI during an active attack. The moment you open a discharge valve without a line connected, that pressure has to go somewhere. Early departments learned this the hard way in the 1800s, when hand-pumped apparatus would blow hose connections across the apparatus floor. The plug is the solution, and it has been standard equipment on every NFPA 1901 compliant truck since the 1991 revision of that standard. Most people see it and think corrosion cap. Engineers see it and think pressure-rated check valve backup. Here is what the plug actually does on a working fire scene. When the engineer, the firefighter running the pump panel, charges the truck's water tank and manifold, every discharge port goes from 0 to 150 PSI almost instantly. Any port without a line attached needs to be capped, or that port becomes a live jet of water at enough force to knock a person off their feet. The brass plug holds that back. The threads are NST, National Standard Thread, also called NH, National Hose, a standard codified after the 1904 Baltimore Fire, when firefighters from outside the city arrived with incompatible fittings and watched 1,500 buildings burn because hoses literally would not connect. NST has a pitch of 8 threads per inch on a 2.5-inch port. That specific geometry creates a seal that holds under dynamic pressure spikes, not just static load. The plug is brass because brass doesn't gall against the aluminum or bronze of the truck fitting. Steel on aluminum seizes. Brass on bronze slides off with one gloved hand. Now look at the industrial fire suppression world, which handles this problem completely differently. Sprinkler systems in warehouses and high-rises use a normally closed valve architecture. Every branch line is capped by a fusible solder link that melts at 155 degrees Fahrenheit, so the system is sealed by default and only opens under heat. No exposed plug, no threads, no human error. Fire trucks cannot use this approach because they need manual control. A firefighter has to be able to connect a line in the dark, in gloves, in 30 seconds. That means exposed threaded ports, which means every unused port needs a physical plug that someone has to remember to reinstall. Industrial systems automate the seal. Mobile apparatus cannot. This is why the NFPA standard doesn't just recommend the plug. It requires a chain or cable tethering the plug to the truck body. Because a plug left on the ground is a dead plug, and a dead plug is a blown discharge at exactly the wrong moment. The deeper reason the plug is brass and not plastic goes back to thermal cycling. A fire truck sits outside in a Wisconsin winter at -20 Fahrenheit, then rolls to a working structure fire where radiant heat at the bumper level can hit 200 degrees. Plastic caps, and some departments used them in the 1970s, crack under that thermal swing. They also deform under UV after 2 or 3 seasons, so the thread engagement drops and the cap can blow off under pressure with no warning. Brass has a coefficient of thermal expansion close enough to the bronze discharge body that the thread fit stays consistent across a 220-degree temperature range. The material choice is not about cost. Raw brass stock costs more per pound than PVC. It is about dimensional stability under conditions that would split a polymer cap in half. Some newer departments use anodized aluminum plugs to save weight on the truck, which matters when you're trying to stay under the 68,000-pound GVW limit on a tiller truck. Aluminum works, but it requires the same anti-galling treatment that the aluminum truck body already has. Otherwise, you're back to a seized fitting at 3 in the morning. The failure case that made all of this explicit happened in 1987 in a Memphis cold storage facility fire. A crew arrived with 2 of their 4 bumper discharge caps missing, both lost during a training drill 2 days earlier that nobody had logged. When the engineer charged the pump to 175 PSI to supply 2 attack lines, the 2 uncapped ports blew open simultaneously. The water loss dropped the manifold pressure enough that the attack lines went from 125 PSI to 60 PSI mid-attack. The crew inside lost effective knockdown capability for 47 seconds, while the engineer manually throttled back and isolated the open ports. 47 seconds is not a long time unless you are inside a cold storage building in a flashover sequence. The post-incident report is public record, and it's the direct citation in the 1991 NFPA 1901 revision requiring tethered caps on all discharge ports. The plug had existed before. The chain became mandatory because of Memphis. This same logic, a passive physical seal rated for the system's working pressure, tethered so it cannot be lost, shows up across high-stakes equipment. Oxygen cylinder valve caps on medical carts, hydraulic test port plugs on aircraft landing gear, the threaded filler cap on a racing fuel cell. Every one of those is a pressure-rated, thermally stable plug on a connection point that defaults to sealed because an open port under pressure is a liability that humans will eventually forget to close. The object is always small. The consequence of losing it is always disproportionate. That tiny brass plug on a fire truck bumper is not hardware store inventory. It is a material science decision, a threading standard born from a 120-year-old urban catastrophe, and a regulatory mandate written because of one bad day in Memphis. The principle is simple. Any pressurized system with a manually operated port needs a rated seal that cannot be lost. If this is your kind of thing, the why behind the everyday object theory drops new ones Monday, Wednesday, and Friday.